Okay. Okay. Good morning, everyone. I'm Supreet Singh Baga. I am Associate Professor at Department of Mechanical Engineering at IIT Delhi. All throughout the day today, I'll talk about microchip electrophoresis and various aspects of microchip electrophoresis, various types of electrophoresis techniques, and how we can simulate these techniques on a computer so that we can design the electrophoresis assays in advance before we go into the laboratory and do the actual experiment. So, the first lecture is on microchip electrophoresis. So, just a quick introduction of microfluidics. So, essentially microfluidics is you can say plumbing in a way on a small scale. So, what I have in my hand is a microfluidic device. This is made in glass and it has a network of microchannels. So, for example, this is how a typical microfluidic device looks like. There are channels made in this device and the device is bonded. So, the only access to these channels is at the ends through these wells or reservoirs. So, what we can do is that we can connect this microfluidic device to the external world through these reservoirs. So, essentially what we have is a piping network on a very small scale. Typically, the channel size is channel width is of the order of 100 micrometers. That is smaller than your hair diameter, or you can say of the order of your diameter of your hair strand, and we can also go to smaller dimensions of 10 micrometers, and we can make these microfluidic devices in various substrates, and that I will talk about towards the end of the day today. And one of the applications of microfluidic devices is to develop point of care medical diagnostic devices. So, the advantage you will see, and there are certainly lot of advantages in miniaturizing electrophoresis systems, and that is how the initial interest in microfluidics started, and thereafter people found additional applications of microfluidics. But the main advantages for us in terms of microchip electrophoresis is that we can significantly reduce the reagent use. Now, we have microchannels whose length is of the order of few centimeters, the width, the diameters, the height are order of 10 to 100 micrometers. So, the volumes that we are talking about are 1 microliter or even in nanoliters. So, that is the amount of liquid that we need, and what we can do is that we can develop portable instruments where this can go as a cartridge and you can do your sample testing on field rather than bringing the samples to the lab. So, this field holds a lot of promise, and microchip electrophoresis is one of the significant successes of the microfluidic technology, which has seen commercialization and it is already in the market, this technology. So, what I will do in today's lecture is to talk about microchip electrophoresis, or essentially those who are familiar with analytical chemistry techniques, how we can integrate capillary zone electrophoresis onto a microfluidic device, and what are the advantages, what we can, why we want to actually reduce the size of a device, and how we can get benefit of that. So, before that we need to understand what goes on when we apply an electric field through an electrolyte solution that fills a capillary. So, for example, I have typically in microchip electrophoresis, this microfluidic device is made of glass. Okay. And here what I am considering is, let us just consider a glass capillary or a glass microchannel, and we fill this glass microchannel with an aqueous electrolyte solution. So, now the surface of glass is actually acidic because of silanol groups. So, you have SiOH groups over here, and in contact with water, glass is actually pretty strong acid in that way. So, it will donate a proton and the surface will acquire negative charges, and that is what happens when you fill your a glass of water. Still you have this negative charge on the surface, but what happens is that on large scales the bulk forces are important, the surface effects are not important. But as we miniaturize the size of our device, the surface effects start becoming prominent. So, what we have now here is we have negative charges which are immobile on the glass surface, and electrolyte has positive and negative charges both, right. So, let us say we have sodium chloride solution or you have some buffer solution. So, what will happen is that negative charges are going to preferentially attract positive charges, okay, and there is also diffusion of charges, okay, diffusion of mobile ions in the electrolyte. But the net result is that you have immobile charges on the surface, but you will have net positive charges near the surface of the capillary. Okay. So, what we get is at equilibrium a diffuse layer of ions where you have more positive ions near the surface than negative ions, because we have to maintain net electroneutrality. Now, this layer where you have more positive charges in the fluid is really small, you can't see it, okay, but the effects of this are what you can observe. So, this layer we call as electric double layer, and typically its thickness is of order of 10 nanometers. So, certainly we can't see it through a microscope, let us say, at such small dimensions. So, what we can think of it is that we have dimensions of 10 micrometers or more of the channel, and 3 orders of magnitude smaller dimensions we have for the electric double layer. So, what you can think is that near the surface you have excess positive charges which can also move. So, this happens when you fill your microchannel with the electrolyte solution. We have not applied any electric field, and this EDL formation you can think of taking place almost instantaneously. Okay. Now, what we do is that through this capillary or microchannel we are going to apply an electric field and see what happens. So, what you can do is you can dip electrodes at the ends of the capillary, in the wells of the capillary that are connecting the capillary, and here I have applied positive voltage and this is negative voltage. So, the electric field is pointing towards the left. Now, there are two things that happen, two transport processes, distinct transport processes that take place upon application of this axial electric field. So, first is that you have these excess positive charges near the channel walls. So, these positive charges, okay, under the effect of the electric field, they start moving and they drag the fluid along. So, what you get is you get a fluid flow just by applying electric field through this channel, and there is no pump involved. Okay. So, what you get is you can think that the walls of the channels are moving and you get a plug shaped velocity profile. So, you can flow liquids just by applying electric fields, there is no need for a pump, okay. And that is the motion of fluid flow, and the velocity at the walls, okay, we can think that the flow is slipping, and this slip velocity is proportional to the electric field. The proportionality constant is called electroosmotic mobility. So, typically what we do is that we apply an electric field of order 10 kilovolts per meter. That means, you have let us say a 1 centimeter long microchannel, then you just have to apply 100 volts to get very high voltage, high electric field of 10 kilovolts per meter. Another effect is electromigration. You have ions in the bulk solution. The ions in the bulk solution are also going to migrate under the effect of electric field. So, the positive ions in the bulk solution are going to move towards the negative ions, and the negative ions are going to move towards the positive electrode. This phenomena is called electrophoresis or electromigration, and the velocity of the ions for small ions typically is also proportional to electric field, and the proportionality constant is called electrophoretic mobility. So, typically if you apply a field of 10 kilovolts per meter, the ion velocity and even the electroosmotic velocity is of this order, about 0.3 millimeters per second. Okay. So, that is the speed that we are talking about. This is the order of magnitude of electric field that we are talking about. So, now what is electrophoresis? So, different ions and ionic species, they have different mobility, and that can be because of various reasons. Some ions are big, some ions have less charge. Large molecules like DNA, they have different mechanism of having differential mobility. If you put a gel or if you put a polymer, these DNA strands will get entangled with these polymers. So, their mobility will become dependent upon the size. Proteins will have different mobility depending upon their the pH of the solution, the isoelectric point. So, for weak acids, weak bases, you can vary the pH and the mobility will change. So, effectively mobility depends upon how much charge you have and what is the mass of the molecule. Now, microchip electrophoresis deals with how we can separate species or analytes from a mixture based on their differential electrophoretic mobility. So, two ions, let us say calcium and magnesium in a solution, let us say a milk sample you want to separate, then we can do so because calcium and magnesium will have different mobility. So, that and how to separate them and how to detect them is what we do in capillary electrophoresis. So, before we go, let me just point out the main difference between electroosmotic flow and the typical flow that we have by pumping. So, if you think that consider that this is a channel and you apply a pressure gradient, you apply high pressure over here and low pressure over here, for example, when we use pumps to flow, then what happens is that here I am showing an experiment where the fluorescent band of a fluorescent dye was initially introduced at the channel inlet, and now you have applied pressure driven, you have applied pressure drop, and now you have pressure driven flow. So, when the flow occurs, fluid flow occurs under pressure, then you get a parabolic velocity profile. So, you have 0 velocity near the walls and the maximum velocity at the channel center, and this is a parabolic shape velocity profile. So, the dye at the center is going to move, but dye at the channel ends, the walls, is not going to move. So, what you will have is you will have distortion of this zone over time, but that does not happen with electroosmotic flow. It appears the walls are not moving, but because the ions are moving, it appears that the flow is plug shaped and the walls are, the flow is slipping at the walls, and you have a band that just propagates or just advects as a band. And in this case, the dye is neutral dye, there is no electrophoresis, this is just due to the flow. But in practice, what we have is that when you apply electric field through a microchannel, you will have both electromigration of ions and also osmotic flow. So, both these motions will be superimposed, and we are going to use both of them for our advantage. So, now we come to microchip electrophoresis, and essentially the principle of microchip electrophoresis is same as what we do in regular electrophoresis, in capillary zone electrophoresis, in gel electrophoresis the medium is different, but otherwise the process is similar. So, what I will focus on is how to integrate this on a microfluidic device. So, rather than talking about the electrophoretic process the capillary zone electrophoresis technique in more detail. So, but let us just recap what is microchip electrophoresis or capillary zone electrophoresis. So, what we do is that consider a single capillary, okay, and this is just a schematic. In later we will use a network of microchannels, but think that there is a capillary in which you fill a background electrolyte solution. Background electrolyte is, let us say, a sodium acetate buffer, for example. Okay, it's a buffer solution with relatively high conductivity, and it maintains the pH of the solution. Okay, and this is important. The conductivity of the solution is governed by the background electrolyte. Now, at the inlet, you introduce your sample whose components you are going to, or whose constituents, the ionic constituents are what we want to separate and detect. So, in my picture over here, I just have two types of ions, okay, two types of analytes, S1 and S2. And of course, I mean, these are not two ions, these are I mean, you have large number of ions of two species, and I am plotting concentration versus the axial location. So, somehow we want to generate an initial condition where you have a background electrolyte and you have your sample at the inlet of the capillary, and the most important thing is that the sample concentration, the analyte concentration, should be significantly lower than the background electrolyte concentration. The reason is that and it will be clear even further that the presence of these sample ions, because these have their own charge mobility, they should not affect the conductivity of the bulk solution. Otherwise, you will have some nonlinear effects. So, now what we do is that we apply voltage. So, what is going to happen? These ions are going to move under the effect of electric field, okay, but all of them are not going to move at the same speed. They have different mobility. Okay. S1, if we say, has higher mobility. So, positive ions will have positive mobility, negative ions will have negative mobility, but I am talking about the when I say mobility is higher and lower, I am just talking about the absolute values. So, S1 has higher mobility. So, the zone of sample S1 races ahead, whereas S2 remains behind. Okay. But that is not the only phenomena that is taking place. As you can see in the pictures in this cartoon, what we have is that while these zones propagate, you also have molecular diffusion. You can't control diffusion. So, these zones become broader and broader, and the peak concentration decreases over time. So, what we do is that we can put a detector over here. As these zones migrate over the detector, you will record some signal, and you can analyze what was the composition of the mixture, provided these samples have different mobility from each other. Okay. So, this phenomena has been is widely used, okay, in analysis of DNAs, RNAs, proteins, small ions for environmental monitoring. You can imagine, there are so many applications for this, and the peaks or the analytes are identified by the location of the peaks and how much time the analyte has taken from the beginning to reach the detector. That is how you detect. Okay, so, this is my a very quick introduction to microchip electrophoresis, but the question is how we can create this condition where on a tiny microfluidic device like this, where you have a sharp initial band and then you can do this separation. So, the way to do it is on a microfluidic device is that we have this cross shaped microfluidic network. So, you have these microfluidic channels where at the ends you have these reservoirs, and just focus on this, we will come back to this later on. So, what we do is that we fill the channel network with the background electrolyte, okay, and then we put the sample that we want to analyze in one of the reservoirs. I will call this as the north reservoirs. This is north, this is south, east and west. So, if you put the sample in the north reservoir, then what we can do is we can dip the electrodes at the end of the the capillaries or the channels, and this is also dipped somehow. There is some issue, this line has shifted, but imagine that this electrode is also dipped. Okay. Now, what we can do is actually this is a resistor network. Okay. It is just a network of resistors. So, I can vary the voltages at the ends and I can control the voltage at the junction. So, what I do is that in the initial step I control the voltages at the ends in a way that the electric field is pointing in this direction. Okay. The junction, the potential at the junction is smaller than the potential over here, it is smaller than this, but it is larger than the voltage applied at the south well. So, what we have is that electric field is pointing in the direction showed in these arrows, and it is going to derive electroosmotic flow. You are also going to have electrophoresis, but in this system let us say that you have very high electroosmotic flow than electrophoretic velocity. So, the sample ions are going to fill the vertical channel. Then what we do is we switch the voltages at the channel ends in a way that the electric field starts pointing from here, from left to the right. Okay. So, we do this. So, the initial band, it disintegrates into multiple zones which we detect. Okay. And the electric field in this separation step in the vertical channels is such that no additional sample enters from these reservoirs. Okay. We will switch the field in a way that we can pinch a sample from the junction. We can just take a pinch of that sample and then it separates into different zones. So, here is a video of this process. Let us okay. So, you will see a video of this process. So, first what you will see is in this particular case for visualization there are two analytes and those are tagged with fluorophores. So, you see this injection step, that is the first step I was showing over here. Okay. And the next step will be the separation step. There is some issue, let us see. Okay. So, in this particular case the channels have a dimension of order 100 micrometers. So, this is the injection step and now you can switch the voltage and you will see that the sample has split up into two zones which keep on migrating, but they also diffuse over time. Okay. So, this is the basic process of microchip electrophoresis. So, our goal is that we want to have as good separation as possible, and what you can do on a microfluidic chip is that you can, here I am showing only 2 peaks, but you can actually separate a very large number of peaks. This is taken from a paper where they use microchip electrophoresis for DNA sequencing on a microfluidic device. And this is one of the major successes of microfluidic technologies, and it is widely commercialized. If you look at a bioanalyzer equipment in your laboratories or in some medical setting, it is actually using microchip electrophoresis, and this is the kind of cartridge that goes into that device. So, the interest in microfluidics initially started just because there was interest in miniaturizing the electrophoresis, microchip electrophoresis systems. So, now what our goal is that throughout this remaining part of this lecture is that how we can improve our separation, okay, how we can get better and better separations through the devices that we have, what kind of parameters we can choose to get better separation. But first we need to define how we say that a particular experiment or particular electrophoresis separation is better than the other. So, we need to define some metrics. So, one is sensitivity, other is resolution. So, consider an experiment. Okay. So, where you have a detector over here which records fluorescence, and let us say we are just talking about analytes which are fluorescent. So, these analytes, they move over the detector and you record the fluorescence versus time. So, this is my electropherogram. Okay. So, this peak corresponds to a species that has higher mobility, because it is reaching the detector in shorter amount of time, smaller time. Okay. So, now we can define sensitivity. So, how low concentration I can detect. So, as I said, the concentrations will decrease over time because your band is diffusing. So, if you have initially high concentration, the signal that you get, the peak signal that you get while when the zone reaches the detector is going to be proportional to the initial concentration. So, how well I can detect that, okay, will determine the sensitivity. If I have a peak which is indistinguishable from the noise in the signal, okay, then you will have low sensitivity. So, I want as high peak value as possible compared with the noise. So, the peak height over the typical noise, you can call it as signal to noise ratio. Okay, that is called sensitivity. But I should also not have a case where you have two peaks which are overlapping. Okay, if the two peaks are overlapping, then there is no point, I mean the separation is not successful. So, we also have to see how well separated two adjacent peaks are. The more this separation between the peaks, the better it is. So, we call that as the peak resolution. So, our goal is to have a certain amount of sensitivity while maximizing our resolution, so that we can clearly identify this peak belongs to a particular different species and this particular peak corresponds to different species. So, the resolution is the distance between two peaks divided by, you can think of this as the sigma is the standard deviation of the peak width, okay, half of the peak width. So, we want to maximize the resolution for a particular, and of course, we also want better and better signal to noise ratio. So, how we can achieve this is what we need to see. Okay. So, now let us focus on the resolution. So, there is little bit of formulas over here, but we can go over them. So, think that your sample 1, the first peak has covered a distance L in time t. Okay. So, what is the speed of this zone is the mobility of sample 1 mu 1 times the electric field. In capillary electrophoresis, the electric field is uniform throughout the channel because the background electrolyte conductivity is much higher. Okay. So, L over the velocity is the time that sample 1 has reached, sample 1 has taken to reach the detector. Okay. During this time, if you have some understanding of diffusion processes, okay, then we know that the peak variance, the standard deviation, the square of the standard deviation of the peak, it actually grows linearly with time. Okay. This is a characteristic of diffusion processes. Okay. Molecular diffusion behaves in this fashion. So, what we get is that the relative distance between two peaks will be, what will it be in time t? This is the relative velocity, the difference between the mobility is time electric field times t is the distance, the separation between the two peaks, and sigma is scales as under root 2 dt. D is the diffusivity of the ions, and let us say we are taking same diffusivity for both the ions. Okay. So, my resolution, okay, scales as, so my resolution, it scales as this, okay, that is the difference in the mobility times electric field, and you have time and time cancels, and you have square root of time over square root of 2 times diffusivity. Okay. This is just a scaling, this is not the exact value.
Can you explain sigma again?
This one?
Yeah.
Yeah. So, the characteristics of a diffusion process. So, see, you have diffusion in various various systems. Okay. I will give you a simple example. So, let us say that I have a rod of metal, or let us say a spoon, okay, and I have a flame, okay, a burner in my kitchen. I put one end of the spoon on the flame. Okay. Now, the question is, after how much time will you feel at the other end that you will start feeling a higher temperature. Okay. So, what happens is heat conduction is also a diffusive process. So, what you see is that if you look at, in that case, the length of your spoon, okay, the time, or you can, the time will depend upon the square of the length of the spoon. That means, if you have 4 times longer spoon or 2 times longer spoon, you will take 4 times more time. Okay. Similarly, in this case we have molecular diffusion. So, if let us say, let us imagine the peak is initially very sharp, okay. It is like a delta function, a very sharp peak. Okay. So, that so sharp that we ignore the initial width. Over time t, the peak standard deviation will scale in this fashion. Okay. The peak width is going to scale as under root of t. Okay. That is the characteristic of a diffusion process. If you solve diffusion equation, okay, you can get this. Okay. But this is just a scaling. Okay. Okay. So, because if you did not have this square root behavior, then things will be very different. Okay. So, what we see is that the peak, the resolution of the separation, okay, obviously depends upon how different the two mobilities are, mu 1 minus mu 2. If it is much higher, you will get better resolution, obviously the peaks will be separated. Okay. If you apply higher electric field, you will get better resolution. If the diffusivity is low, for example, when you have you do electrophoresis of DNA strands on a gel, in that the diffusivity is very low. So, the resolution is good, and if you do the separation for longer time, the distance is going to increase, okay, much faster than the peak width is going to diffuse. Okay. So, this is about resolution, this is not about the sensitivity, because you can, what this says is that if you have separation for a longer time, okay, you can get better and better resolution, but your peak is also diminishing over time, because the peak is diffusing. So, the sensitivity is also going to go down. So, there is a trade off, okay, between resolution and sensitivity. And if you do further analysis, what you will see is that the the time is related to the length, okay, this peak takes to reach the detector, okay, or the length of the channel. So, if you put this expression of time, what you see is that the peak resolution actually depends, okay, besides the mobility and diffusivity, depends only on the applied voltage, okay, because this electric field times length becomes voltage. So, all that matters is you take as long whatever length you want, okay, as if you apply a high voltage, you are going to get high resolution. So, what happens is that glass has some conductivity, it is not very high conductivity, but certainly higher conductivity than plastics, and on a planar device, if you can apply very high voltage, the heat dissipation you can still control, and you can also put cooling blocks because of the planar geometry. So, in microfluidic devices we can use very high voltages, okay, and it really does not matter you want a 1 meter length or a small length, the resolution will be similar, okay, if you apply similar magnitude of voltage. Okay. So, this is how we want to improve the resolution. We want to apply high voltages and resolution increases over time. But there are various mechanisms that occur, transport processes occur during the electrophoresis process, which can lead to reduction in the resolution. Okay. How we can have lower resolution? Okay. The main reason for reduced resolution is that there are some transport processes which are trying to increase the width of the zone. Okay. So, if these peaks are dispersing, then you will have lower resolution, because resolution is defined as the relative distance divided by the peak width. Okay. Another term is used in electrophoresis literature called plate height, but see, this is not a dimensionless quantity. So, personally I prefer resolution, because it is a dimensionless quantity, you have length over length. Okay. So, now we have to see what are the various ways by which, in addition to diffusion, the peak can diffuse further. So, if you have, in addition to electroosmotic flow, you have non-uniform flow in your capillary. Okay. This could be due to imbalance of fluid on both sides of the capillary. Sometimes you also have Joule heating that can lead to some non-uniform flow. Then what you can have is, you can have additional dispersion of the analyte peaks. Okay. And this mechanism that I am showing here is called Taylor-Harris dispersion. Okay. And you can work out the effective diffusivity. The effective diffusivity is that if there was no flow, then what would be the diffusivity? Diffusivity is D, but if there is a flow, the effective diffusivity will be much higher. Okay. We can work out this, but today I am just going to explain the mechanism of Taylor-Harris dispersion. So, let us see. So, you start with a straight band, and let us say you apply a non-uniform flow. So, what will happen? The solute in the middle is going to move ahead, whereas the solute at the channel walls is going to stay there, because my pressure driven flow has 0 velocities at the end. It is not like electroosmotic flow velocity, plug shaped velocity. So, you will have this distortion of a band. So, essentially the molecules in the middle are going to get advected, the molecules at the ends are not going to get advected. Now, what happens is that you have very high vertical concentration gradients. So, now you have very strong diffusion along the radial direction. So, over time, okay, just because of the combination of advection in the axial direction and diffusion in the radial direction, this band is actually going to diffuse even further. In fact, if you have an analyte with lower diffusivity, it is going to have higher dispersion, okay, because first it is going to the band is going to distort much further, much much more, and there are going to be very strong radial gradients. So, the goal is that in microchip electrophoresis we want to avoid non-uniform flow. Okay. We want to avoid concentration gradients, we want to avoid Joule heating. All of those can lead to non-uniform flow, which can lead to additional dispersion. That is one thing. Now, we can look at the competition between signal to noise versus resolution. So, what I told about resolution was I just gave you an insight, but in an actual process, okay, you can have the peak actually variance or the peak width depends on various factors. Okay. The peak width depends upon the amount of sample that you have injected. If the plug is initially wide, then the final peak is also going to be wide. Okay. That is the first term over here. Okay. This is due to dispersion. Dispersion could be, it's again a diffusion phenomena, but now I will replace diffusivity with effective diffusivity. The first one is the variance of a plug of half width h, okay. And then you have some variance, some peak width due to the detector width also. So, imagine like this, okay. I have a detector of finite size and there is a thin line, that thin band that is moving over the detector. Just because my detector is wide, okay, it's also your thin band is not going to appear to be thin, it's going to be appear to be diffused, okay. Just like you have a frosted glass and you shine a laser pointer from the back, it's the pointer is going to look a bit more diffuse. So, this is this term, okay. So, if you incorporate all of these things in the model, okay. So, what you can see is that, okay, this dotted line is I am plotting signal to noise ratio versus length, and I have non-dimensionalized the length with the detector width, okay. This I have taken from it this from a model, but qualitatively is what you can understand. So, you all understand that signal to noise ratio is going to reduce over time. The noise remains the same in the detector, but the peak is going to diffuse over time, okay. Peak cannot increase, otherwise it will violate the second law, okay, of thermodynamics. So, you can only have entropy is only going to increase, you will have more diffusion over time, okay. Whereas the resolution keeps on increasing over time. So, what we have to do is that we want good resolution and good signal to noise. So, if you plot the signal to noise and resolution on an axis where you have on the vertical axis the initial plug width versus the length to the detector, you will get a diagram like this, okay. And there is only a particular zone where you can get good signal to noise ratio and good resolution, okay. To understand this, first we know that if you are over here, okay, and you keep on increasing for a given plug width of the initial sample, okay, if you increase the length, the resolution is going to improve, but the signal to noise ratio is going to decrease, okay. If you have a fixed length of the capillary till the detector and you increase the plug width, imagine that the initial plug width is so high that, okay, so let us say the initial plug width is so high, despite the fact that these two zones are trying to separate, they are still not able to separate until they reach the final reach the detector. So, higher plug width is going to also reduce the resolution. So, there is a region where you can get good signal to noise ratio and good resolution, because signal to noise ratio also or sensitivity also depends on the plug width. Imagine you add a very tiny plug of the sample, it is going to diffuse fast, but if you have larger sample you will still have the peak intensity will still be large when the sample reaches the detector. So, just to recap and qualitatively show, so this is a video that we captured in our lab. This is also capillary electrophoresis. So, I mean, because of the light you can't see, but there are two plugs that are going, okay, towards the right. So, as you can see, initially so this is the initial plug width and the zones are separating, but the sensitivity is decreasing over time, okay. So, now what we can do is we can try to use other ways for optimizing the electrophoresis process. So, we know that the initial plug width is also an important factor to improve the resolution. So, if in this experiment what you see is that the initial plug is a bit wide and also a bit distorted. So, there is a lot of work that has gone into how to optimize this injection step, so that you can have a very uniform initial plug width, okay. And this is this is one way you can do. There are various ways to do it, but one easy way to do it is that you have 3 steps of your electrophoresis, 3 steps of voltage application of voltage. So, 3 voltage schemes that we do. So, the first step is the pinching step that you see over here also, that the sample is actually moving to the waste reservoir, that creates an initial condition like this, which we have seen in our videos. Okay. Then you momentarily reverse the flow in the vertical channels. If you momentarily, so you see that you have this trapezoid shaped plug initially. I want a very narrow and straight plug. So, you can reverse the flow, so that the flow momentarily goes towards the north reservoir, okay, and that we can do by managing the voltages at the ends. So, this flow reversal will lead to a sharp, or you can say straight plug initially, and then you switch the field towards the right, and then you have separation. So, lot of work has gone into optimization of injection step. Other way of doing it is to modify the device, so that you do not have this cross. There is some other geometries which will give you better injection. Another source of dispersion in electrophoresis is that you have turns in your microchannel. So, we know that if we separate over longer distances and higher voltages, we can have better and better resolution. So, if I have a microfluidic device which has a turn, okay, now that is going to lead to sphere peak dispersion. So, the reason is that if you look at this picture over here, okay, you can think that the easy way to think is that the molecules or the ions that are closer to the inner turn, okay, they have to traverse a smaller distance, or the velocity is the same, but just like in athletics, okay, these ions are going to race ahead, okay, because they have to cover a shorter distance, okay, and these ions will lag behind because they have to cover larger distance. So, what happens is that if we do electrophoresis and we have turn in a microchannel, in a hope that we can have longer and longer channels on a smaller device, then what will happen is that you will get a sphere peak distortion like this, okay, and this peak distortion will not correct itself. In fact, now you have gradients in the radial direction or the widthwise direction, you will have diffusion in this direction, and eventually the zone will become this wide. Okay. So, this is what we want to avoid. So, one way to avoid is to optimize the turns. First, you do not have turns. If you have, okay, you have to optimize the turn geometry. So, what you can do is, the easy idea is that, okay, you have the arc length, let us say you go from this point to this point, you design your geometry so that the distance that ions have to travel, okay, from the edge, from the outer edge and the inner edge is the same. Okay. So, it is a clever trick by which you can significantly reduce the peak distortion. So, anything that we can do to reduce the dispersion of the zones is going to improve the resolution of our separation. Okay. Now, coming to the last point, this is called electromigration dispersion, okay, and you will understand it better when we discuss nonlinear electrophoresis techniques like isotachophoresis in the forthcoming lectures. But just to give you a brief idea, a rough idea of what this dispersion is, that initially in the lecture I said that the background electrolyte concentration should be, or conductivity should be, much higher than the sample concentrations. The idea is that the presence of sample in a particular region, or the ions in particular region, should not modify the conductivity, because if you modify the electrical conductivity of the solution locally, it is going to change the local electric field, and it is going to change the speed at which the ions are going to migrate. Okay. So, I am going to show you a simulation, okay, because I like simulations. I think it's a very nice way to illustrate and teach electrophoresis. So, what I am doing over here is, in this simulation, we have a background electrolyte comprising of 12 millimolar trace and 20 millimolar acetic acid. We have two analytes injected at the inlet, one is pyridine, other is aniline, and let us see how the separation takes place. Oh. There's some. Sorry, there is some issue. Okay. So, it is the same simulation. So, what you see is that if the initial analyte concentrations are low, these two peaks remain Gaussian shaped peaks, and you have this separation. Okay. But if the initial concentration of these two peaks, the analytes, is high. So, you have 2 millimolar. Okay. Then what will happen is that as these zones migrate, they are also going to change the local electrical conductivity of the solution, that is going to in turn affect the electromigration speed. So, what you will see is that here the zones were Gaussian shaped, as you would expect from a diffusive process, but here what you see is you have triangular shaped, or the zone width has increased. Okay. This has led to dispersion. The reason is this: the electric field, for these particular analytes, the electric field in the region where you have these peaks is higher than the electric field outside. So, what happens is the ions over here are moving faster than the ions moving ahead of it. So, this interface sharpens, whereas the ions over here are moving faster than the ions behind it. So, that interface becomes broader. We will discuss this more in the next lecture, but you can have electromigration dispersion, which can lead to further decrease in the resolution. Okay. So, that is why initially I said for microchip electrophoresis, the initial sample concentration should be significantly lower than the concentration of the background electrolytes. Okay. Now, there is another way by which, typically it is an easy way, but it also has some drawbacks of increasing the resolution of increasing the sensitivity of the separation. So, what we do is we use a technique called field amplified sample stacking. So, just focus on this picture over here. So, imagine that you have somehow you generate a concentration gradient in the background electrolyte. So, you have high conductivity solution over here and low conductivity solution over here, and you have negative ions over here, okay, and you apply electric field along this direction. So, the negative ions want to move ahead. Okay. So, now what happens is that from Ohm's law, electric field is inversely proportional to the local electrical conductivity of the solution. Electric field is actually the current density over divided by the conductivity. So, in high conductivity solution, the electric field is less, in low conductivity solution the electric field is high. So, what these ions, while they move towards the left, they feel that the ions in front of them, once they reach the high conductivity zone, have low velocity, while they are coming at very high velocity from behind. It is just like you have a traffic jam in front. So, what will happen? These ions are going to pile up at that interface. So, the concentration will increase over time. So, here I am showing this experiment. So, what you see is, look at this. Here the ions are moving towards the left, but electroosmotic flow is moving, taking everything towards the right. So, you see that the initial concentration was low, but the concentration of the fluorescent species has increased over time, and what you see, the motion towards the right is due to the flow, not due to motion of ions. The ions are moving towards the left, electroosmotic flow is carrying towards the right. So, what we have done is the initial concentration we have increased, okay. We have pre-concentrated the sample. Okay. Now, what we can do is we can combine this field amplified sample stacking with capillary electrophoresis. So, what we are going to do is that we are going to have a low conductivity sample and a high conductivity background. Okay. So, now this initial sample over here was of lower conductivity. So, initially the concentration increases, but then you will have separation. Okay. In a later lecture, I will show a detailed simulation of how we can design this process, but we can increase the sensitivity, because first we are trying to stack the samples and then we are going to do separation of these species. So, with this we come to the end of this lecture. So, I hope by through this lecture you have understood how we can use a cross shaped microchannel to perform capillary zone electrophoresis. I have tried to show that there is a trade off between resolution and sensitivity. You want to have as much peak separation as you want, but if you want to increase the resolution, the peaks are going to diffuse further. So, the sensitivity will decrease over time. So, we need to do an optimization to find where we can get good resolution and good peak sensitivity. We have seen that there are various ways by which you can have decrease in the separation resolution because of dispersion of sample zones. One is that you can have non-uniform pressure driven flow, which can lead to Taylor dispersion. Okay. Then we have the initial plug width is also going to affect the resolution. So, we can control the initial plug width. Any geometric defects or turns in the geometries or the channels are going to lead to dispersion. And finally, we have touched upon a phenomena called electromigration dispersion, which is a nonlinear electrophoresis phenomena, which we will discuss in far more detail in the forthcoming lectures. What I have not discussed in the initial lectures are what are the ways we can detect the samples. So, in the next lecture on ITP, we will look at some detection methods. So, the same detection methods apply to any electrophoresis technique. So, I have moved that part to the next lecture. So, with this we will come to end of this lecture. If you have any questions, I will be happy to take any questions.
The last aspect is not very clear.
Yeah, that I will. I just touched upon that. I will explain it in more detail. Okay, later on. So, the idea is that the initial sample. Let me go back and. So, the way to implement that is that this sample, okay, the conductivity you can take low conductivity than the background conductivity. So, what will happen is that in this initial step you have high electric field here and low electric field over here. So, these ions are first going to stack together and the concentration is momentarily going to increase. So, you start, even though the initial concentration of the ions is low, you increase the concentration before separation. So, that we will discuss in later lectures. Okay. If any other question? So, if no more questions, then we can stop here, right?
These kind of principles are working into that sugar testing and
no. So, sugar, that glucose testing
strips and
no. So, glucose testing is based on electrochemical detection. Okay. Yeah. So, there you have if I am correct, there is an enzyme called glucose oxidase, okay, and there is an electrode. So, when the oxidation process takes place, so you have oxidation is what? Loss of electrons. So, electrons flow through the circuit and you count what is the charge that is transferred. So, that is a completely different process. Here that is an electrochemical process on the electrode. We are talking about the motion of ions within the bulk solution. The only electrochemical reactions that are taking place are at the electrode, which will lead to electrolysis. Okay. Yeah. Okay, so we can stop here. Yeah.
I'm not sure if there's morning tea with tea today or not. The other days there was around 11.